As we basically always do. This one is titled Towards the Science of AI Agent Reliability. I will say I think this paper is very good. I think it is quite ambitious. I think it is introducing a fruitful paradigm, which is a pretty high bar for a publication. Um, and yeah, and I think they do a quite good job. Maybe at the end we can talk about quibbles and such, but I think it is probably a lot to ask of a paper to introduce a paradigm and not be subject to some quibbling around the margins. Anyway, with that, um, I don't know, vote of confidence on my part. I will go ahead and get started into the substance of the paper. Okay, so reliability appears in the title, and you might wonder, like, I'm gonna go ahead and like Uh, I might delete some things because we're starting a little bit late and this is a little bit verbose. So just pretend I don't do that if you see me do it. Um, so anyway, so what's up with reliability? I will say that they frame this in a little bit of a grandiose way. They call this like a core shift in perspective, and then later throughout the paper, they'll talk about like a fundamental rethinking of all benchmarks. So I do bracket that a little bit. I mean, this is like these are academics, so need like grants and such. So of course they're it's just I guess it's an occupational hazard to what they're doing. Um, but with that said, I think it is, like I said, pretty paradigmatic where before you would talk about, or the discipline would talk about how often an agent succeeds at some task. And then in this framework, they talk about how reliable it is. And we're going to see facets of this later. But to preview them, we could say how predictably, consistently, robustly, and safely does the agent behave. Um, so Right. Some people might say that like this is actually not an issue, just as um, capabilities and like accuracy goes to 100%, so will reliability. Um, that is kind of this like practically vacuous claim. Um, so like that is true analytically, that a model that never errs will be 100% reliable, but that is just like not going to be the case ever. So again, we don't like need to rely too much on these like mathematical arguments that are not going to have real world uh, application. And previewing a little bit what the results say or what they find in the results, these two dimensions are just empirically distinct from one another. Although there maybe we can have some like quibbles about this. Um, and I'm just gonna highlight one thing here, and that is that at the same time that in the limit, these two things go hand in hand, like 100% accuracy does entail 100% reliability. At any point under 100% accuracy, two models with a given accuracy, such that that accuracy is less than 100%, can have very different reliability profiles and reliability scores. So they are also like analytically separate as well. I think I would encourage you to read the paper for these real world failures. I'm not going to open this up because I don't know. I want to motivate you to actually go read the paper if you haven't. If you have read the paper, then it's redundant for me to talk about these. But there are some pretty illustrative ones. I will say though, as I read them, sometimes they do kind of seem like capabilities things. So take that with a grain of salt, I think. That's like worth having some thoughts about. Maybe we can talk about that in the discussion. Um, but yeah, there were some pretty newsworthy, some pretty like splashy items in the news about the real world failures that like make you think about reliability. Okay, so a fundamental perspective in this paper is this idea of safety critical engineering. And I understand that we're in the Blue Dot world right now, like the Blue Dot ecosystem, but the Center for AI Safety also does courses. And if you are interested in this kind of thing, um, Dan Hendricks, who founded and runs the Center for AI Safety, has a textbook on AI safety. and there's an associated course, and it's very much into safety critical engineering, systems thinking, and the like. So that's just a little shout out to that. Um, and okay, and so that book and then this paper are inspired by these like disciplines where things can go really wrong, and you have to have like a lot of safety measures in place. And so the authors of this paper, after sort of an implied reading of, like again, aviation, nuclear power, automotive, industrial process control literatures, they abstracted these different dimensions of reliability. So next to these, I listed some examples, um, and below I'm going to show you some like snappy definitions, as well as operationalizations. These are consistency, robustness, predictability, and safety. Um, I'm actually going to skip these examples. So again, I think the paper is really good. You should like read these to see how different industries implement them concretely, but I'll just go to what they mean um, for the sake of time. So consistency is consistency, like has similarity across runs to not use exactly the same word. Robustness is withstanding perturbation. Sometimes you'll hear this called fault tolerance. Failing predictably means failing in a way that the model can predict. So um, I think this one maybe is one like um, I would just call it calibration. And in fact, that's what it turns out to be. I'll explain a little bit more what that means in a second. And safety is having, they mention this as having bounded error severity, is what safety is. But again, when we take apart safety into two dimensions, it'll be a little bit more clear what that means. And so here you notice that there are like four parts to reliability, with a caveat that in the end they actually will not include safety in the reliability metric. But so those are only four, and they actually have 12 separate metrics that will be aggregated into these four. So again, they decompose reliability into three or four metrics, and then those four metrics themselves have decompositions that I think are illustrative enough, useful enough that I will mention them in a second. Um, One thing that's useful to note is that for the purposes of generating a single number to like plot on graphs and talk about change over time, they will create an overall reliability score. So again, so after this decomposition process, they recompose everything into a single number that is just a weighted average where where the three dimensions they include get equal weights. So again, that's our consistency, robustness, and predictability. Um, and safety is going to be excluded from the aggregate. And maybe that's something we can talk about in the end. Their argument for this is that tail risks shouldn't be averaged away. Um, I don't know if I'm 100% convinced by this, but that's fine. I think one of the things that they do that's nice is they give us like this big resource. And like if we were running some process where, for example, predictability was less important, then we could like take it out of this. So that is a really nice thing about having been so exhaustive and developed like submeasures um, of reliability, as opposed to just having one number from the beginning. Okay, so I'm gonna go through these now one by one. And I will say, I'm going to spend most of my time, I think, talking about the framework because that's what's useful in this. I think that the particular models they run and the results even are like they can they're interesting, but again, what I think this paper is really contributing is the framework. So that's why I'm going to prioritize that. Um, but well, I guess I don't know. You're stuck with me doing that since I am driving this car, as it were. Um, okay, so consistency is one of these. Don't worry about like these complicated looking formulae. Um, they're just here, kind of for my notes. You're not supposed to like immediately look at this and understand what's going on. Um, so yeah, so again, so don't worry about that. So outcome consistency is basically just does the agent succeed or fail the same way each time. So basically, you could have in some aggregate, you could have a success rate of 80%, but maybe it fails like, um, you could imagine two different agents. You could have one agent on a task of, so like a group of tasks, a group of 10 tasks, and it consistently succeeds at eight of them and fails at the same two. So again, success on the same eight, failure on the same two. Or you could have an agent who on average scores 8 out of 10, but will like change the ones that it succeeds and fails on. And so outcome consistency is a measure of that. Like to what extent does it fail on the same problems versus different problems? And don't worry about like max Bernoulli variance as a normalization. So there's that. And then there are two other ways of operationalizing consistency, and those are different measures of the trajectory. So these are agents, and I guess we don't have time to like get into the whole like what is an agent, right? But the agents can make use of tools. In fact, agents do make use of tools. That's one of the defining characteristics. And so basically a trajectory consistency looks at do they use the same tools to solve the same tasks or do they like do different things each time? And there's a distributional sense and a sequential sense. So the distributional sense you could think of as like less strict. It's just like were the same tools used? And the sequential sense of consistency is like did they use them in the same order? Um, so yeah. So these are the three. And oh, and then sorry, there's that fourth one actually. There's resource consistency. And this is just is like the token usage the same each time? Or does it sometimes use like 10x the tokens to solve the same task? Um, these ultimately will get bundled together so into like outcome and trajectory and resource, and trajectory itself is an aggregate of these. So don't worry too much about this. These are done so that it doesn't, so that consistency doesn't like outweigh the other dimensions just because it has more subdimensions. So again, if that goes by too quickly, don't worry about that. But just know that the aggregate number is consists of these subdimensions. All of them are like pretty thoughtful, I think. So that's consistency. Robustness. Um, they have like a fault robustness. They have an environmental robustness and a prompt robustness. So fault robustness is measured by looking at does the model recover when the experimenters um, modify things in certain ways that the model was not expecting. So three examples are API timeouts. So they might induce pauses. They might like, I don't know, remove a parenthesis or a bracket somewhere, and that would give rise to a malformed response. They might have like a service unavailability thing, right? So we've probably all encountered like HTML errors, and because one of the tasks, the Gaia task, requires using the internet, right? That's like a pretty realistic thing. So yeah, so there's a fault robustness, there's an environmental robustness, where things are changing in the world, and they want to see if models can recover from that. So, for example, I use Claude Code, and Claude Code, when it was being trained, I guess this was when Opus 4.6 was being trained, the OpenAI models had a certain like API structure, but then these API parameters have been renamed. And so every time I want the model, I want Claude to call an OpenAI model, it will fail because of this renaming. So then it has to go and look up what the current API parameters are named. So in that sense, Claude Code is robust, even if it is a bit frustrating from a user perspective that it does have to fail every time. Okay, so that's environmental robustness. And then prompt robustness is, and I'll just read this, invariance to semantically equivalent reformulations of instructions. Um, so, right, so models should be able to extract the tasks from a prompt, regardless of the exact phrasing of the prompt. And then these things are going to be aggregated into a single top-line measure of reliability version robustness. So there are those. Later we can talk about these, like how this was calculated if you want, but I will move on for now. Um, right, now at the halfway point. So the next dimension of reliability is predictability. Um, and I think I might skip this because in the end, they will just use the thing called a Brier score, which, if you are familiar with things like linear regression, which is an optimization method for minimizing the sum of squared errors of prediction, that's what this is. And if you're not familiar with linear regression and minimizing the sum of squared errors, then basically what this is trying to do, what this calibration measure, which again they call predictability, just means like, can the model guess how likely it is that how likely it is to have gotten the answer correct? So if it says like 20%, um, it will, and then on 20% of those tasks, it did get the answer right, like that will be good. Whereas if it said 20%, but actually it's like 80% of those tasks it gets right, then it would be miscalibrated. And I just elided over a lot of details, but that's the idea. Can the model predict how likely it was to have been correct? Okay. And then safety, again, this one is a little bit different. This dimension is a little bit different than the other three in that it will not be aggregated with the other three, but it is probably as important, if not more, um, at least from certain perspectives. So there are two submetrics to safety. One measures the frequency with which the model fails to comply with certain just guardrails, like does it stay within the guardrails or not, regardless of the consequence, and then the severity of a certain violation. So, getting ahead of myself a little bit, one of these benchmarks, the Tau benchmark, has a part where it's like looking at where it's simulating an airline customer service situation. And for example, if an airline agent skips identity verification because the caller volunteers a booking reference, that would be a compliance violation, even if we're assuming in this case that that was all genuine, like there was no sort of stolen identity thing going on. Um, so anyways, that would be a compliance violation, and that would be like bad for safety. But again, there was zero harm in that case. And in the other case, the other subdimension of safety, we do actually look at harm severity. And so the idea is like conditional on a violation occurring. How severe is it? Again, please do not spend too much time looking at this LaTeX. Um, but the idea is that, you might have some type of like safety violation, but they could be like have very different consequences and they should not be counted as the same. The example they give is one agent misnaming folders versus an agent that like permanently deletes documents. And yeah, these are pretty different from each other. So severity is like a pretty important subdimension um, of reliability. Okay, those are the four subdimensions. Um, Trying to think. If there are any questions, I would feel fine taking them now. Otherwise, I'll very quickly go through the test beds and the results. So we have some time for discussion. Yes. All right. Andre, feel free to go ahead.
Yes. Could you repeat what is predictability like in short?
What is predictability in short? Is that what you said?
Yeah. Yeah, I mean, just in few words.
Um, yeah. So I mean, at a very mechanical level, this is what it is. So, I'm trying to think if I can do this quickly. So, um, so this Y is if a model, it can be one or zero. It's a binary variable in this case because we're judging correctness. So let's say that like yeah, sorry, as I'm saying this, I'm thinking like, oh man, how many people am I going to lose as I go through this? So I'll try to do this quickly. So if this is one, if the model ends up being correct, but its prediction had been where the CI is, if this prediction had been zero point 0.2, right, then this internal part would be negative zero point 0.8, and then that gets squared, and then that's like bad because so you get 0.64 and then there's this t term and like that is just like over all the predictions that you make. And so the way that you could have a perfect calibration of one is just to know with certainty like whether or not you're going to be correct. So say for example, this is probably the example I should have started with. Say I say one and one being I got this correct and I'm saying this with 100% certainty. This will become zero. This whole sum will become zero. And if I'm always 100% correct, then all of this will be zero. And my Breyer score, which is an operationalization of my calibration, which they're using to operationalize predictability, will be one, which is perfect. Um, so yeah, so I think I might leave it there
So,
just because I don't think I'm going to elucidate this much more right
yeah,
now. But
just
basically,
just a
go
short
ahead.
question. Is it connected with introspection? I'm just trying to get it around.
Yeah.
Yes, it does require a model being able to. I don't know if interest. I mean,
But when you're talking about that equation, you're talking about the model's prediction of its own accuracy, right? Because in theory, um, uh, predictability could be, some other model or some other process that is predicting what the outcome is and whether the model would get it right or wrong. But in this case, they're specifically talking about whether the model itself can predict its own answers. Is that correct?
so yes, although with one caveat, which is, and this was a note I had for discussion, but I guess I'll bring it up now. If I'm not mistaken, the CI term, which is the model's prediction for if or what probability it gives to having been correct on a given problem. This number was generated from the model after seeing its entire trajectory, which to me seems like the wrong time to do it. I think the right time to do it would be before it has even started the problem. And that would be an introspection problem. Whereas I think the way it was done, if it's done the way that I think it was done, it is more about can it look at a trajectory and say, is this trajectory giving me the right answer? In which case you could have another model looking at, so you could have model J looking at model I's trajectory. So, so yeah, so with that caveat, which is I think a pretty significant caveat, I guess we could say it's introspection. But uh, anyway, so yeah, that was one of my little um, disagreements with the paper. Although maybe I misunderstood this and read it too quickly. It is a quite long paper. It's 66 pages, and I actually did try to read a decent amount of the appendix. So anyway, if someone wants to look this up as I go through the rest of this, that might not be the best use of your time, but I would appreciate it. Um, okay. All right, I'm gonna go through this really quickly. Um, so the Gaia. test bed slash benchmark has nothing to do with like Mother Earth, which is what Gaia refers to usually, or something like that. It just stands for General AI Assistance. It was put out by Meta back in 2023. Um, and one of the most famous author on this paper is Jan LeCun, but he's not the first author, so he does not appear there. Again, I'm going to go through this really quickly. So in these tasks, there's going to be a system prompt. Don't worry too much about this. But a question would be something like, there's an attached Excel file, description, and then ask a question like, what were the total sales that the chain made from food, not including drinks, and then some formatting uh, specification. And then here's just showing like what that would look like. So in this case, it's using pandas to manipulate the file and get out the answer. So yeah, so there's that. And one important thing to note is that there's like a deterministic way of checking answers. So there's no like LLM as judge stuff going on. It's also binary, so it's correct or not. Um, and then the only other thing I'll mention is that there are like different levels of difficulty. So these Gaia tasks vary in terms of how many steps are needed, whether or not, how complicated a tool use is, and the amount of reasoning involved. So that's Gaia. And then Taubench, just really briefly, involves so an LLM simulating a human. Although I guess now with like agent to agent stuff, it could, you know, be somebody's agent, in which case it's no longer simulating human, and it's fine that it's an LLM. In case you're wondering why it's called Tau, like what's up, why is it Greek? Tau is just itself an acronym for Tool Agent User Interaction Benchmark. Um, and so the stuff I'll talk about, I think, is like flight bookings. Um, yeah, there's a funny sociological thing about the fact that there were only 50 tasks in this benchmark, which is like really small for a benchmark. And most of them were, sorry, almost half of them were actually like flawed. So that says something that's pretty sad about the state of benchmark creation, but I will not dwell on that right now. So that was Talbench. And Talbench, by the way, is the where like safety issues are going to come from. Like it's unclear how you could have like a safety issue with Gaia because you're just looking up facts. But with Talbench, you could expose somebody's private information. You could I don't know, book an incorrect flight or something like this. So those are the two test beds. Um, and I want to cover this. No. I will just say very, very briefly that they tested up to pretty recent models. So the most recent models here came out in December 2025. So I mean, in these 3 months, we have moved on to Claude 4.6, and we've also moved on to GPT 5.4. But yeah, I mean, pretty up to date, at least as far as these things go. Um, and they also have a special harness. Or agent scaffold that I'm not going to talk about. But if you're wondering why, for example, there's not like Codex for OpenAI or Claude Code for Anthropic, it is because that would introduce quite a few complications because they have this thing where their harness allows them to calculate like exactly the amount of tokens used. That is really nice for this, but you know, if you're in the social sciences, you might be like, I don't know what the ecological validity of this um, researcher developed harness is now that companies are developing their own agent scaffolds. Okay, so let me close out this here and then go to results in the remaining time. So this I thought was like kind of a funny publication thing. Like this is from the results, but it's also on the very first page of the publication. So I had never seen that before. But anyway, yes. So these are the results, and you can see on the side. Let me see if I can make this a little bigger. Yes. So they disaggregate by benchmark. But basically what you see is on the x-axis you have time, and that just refers to when the model was released. And then on the y-axis you have, well, it depends, it varies from these from plot to plot, but you can see like that over time accuracy. So this first column on the left is accuracy, and accuracy has been increasing. Um, I mean, there's obviously variation around that straight line that they've drawn, um, but yeah, the trend is upward, and so these two slopes just, I think, probably very coincidentally have been 0.21. So that would be, given that, I think this. Well, anyway, so 0.21 per year. So like accuracy, is increasing by 20 percentage points per year. That's a pretty steady clip, especially since, starting from an accuracy of 0 and increasing by 0.21 per year would get you from 0 to 100 in only 5 years. Of course, that's not how the world works, but anyway. Anyway, the point is pretty quick. But the juxtaposition is that reliability has been increasing much less. So, very starkly in the case of the Gaia benchmark, um, there's basically a zero slope. So it is very slightly positive. It's 0.03, which is very close to 0.00. Um, so yeah, not a huge increase there. The reliability increase for Tau bench has gone up, but it's pretty low. Um, and the last group of plots on the right-hand side, the column, shows the relationship between the two. So if they increased hand in hand, right, you'd expect something like a slope of 1. The slope is not 1. Now, this is gonna make this comment I'm about to make is a bit editorializing, so it's maybe like discussion-y comment, but like, I mean, reliability was already at 0.8, so if it had increased 0.21, like accuracy had, like it would be at 100% now. So I mean, I'm a little bit unclear on like exactly what to make of this uh, headline finding. I mean, it is notable that it like basically did not increase on Gaia, but it's kind of unclear like what it should be in some sense of should. Um, so yeah, so these are the top line findings. Then when we break it down again, because that was this overall metric, which, as you may remember, consists of three things. So I'll go through those right now extremely briefly, since, well, I guess this meeting can spill over a little bit past the hour, but still, I'll try to, uh, you know, not abuse presenters' prerogative too much. So consistency, which again has three measures, three submeasures: outcome consistency, trajectory, and resource consistency. You can see again, okay, sorry, this is not over time. Now this is broken down by model. Um, yeah, this is what these look like. I'm trying to think if there's, um, I don't know. So, is there anything to say about these? I will say, um, this one I think maybe was one of the more surprising things, that outcome consistency is low across models. I'm a little bit surprised by this. No, so that is what this is. This is a particular subdimension of consistency. Um, yeah. That said, like you do see, for example, if you look at Anthropic's models, I mean, Claude 4.5 Opus is quite a bit more consistent than like an older version of Claude Sonnet or Haiku. So yeah, so it does increase, although, for example, with the OpenAI models, there's actually not. I mean, for some reason, 5.2 is just as consistent as, sorry, 5.2 reasoning is less consistent than 5.2 and is as consistent as GPT-4 Turbo, which is now a very, very old model. So that's kind of weird. I haven't thought about that too much. Um, but it is a thing that they observe. There's no plot for trajectory consistencies, but they do find substantially higher distributional trajectory consistency than sequence. So again, so like what tools are used, what steps are taken, can be the same even if the order is different, is what they find. Yeah, I'll leave consistency there for now. Prompt robustness, which is one form of robustness, let's see, has gotten higher. Let me just look at Anthropic models. Um, so yeah, like the oldest version of Haiku was, significantly less robust than more modern and bigger models. So that is observed. Yeah, and I will say one thing you might be thinking about with prompt robustness is there's like this whole area of prompt engineering. And in theory, uh, okay, that's a little bit different than this. So in prompt engineering, you might actually make non-semantically equivalent statements. Um, and in this case, like these are supposed to be essentially the same prompt, just with like typos and ordering things in a different way. So these are like slightly different things. Um, Whereas, yeah, so prompt engineering, like you might actually introduce like semantic differences between two prompts. Although like you would also talk about ordering effects and whatnot. But maybe in the discussion we can talk about this a little more. And then do I want to cover this? Yeah, okay. Really briefly, top line thing with calibration is that it has improved noticeably. I didn't cover what discrimination was, so I will not talk about that. But predictability is important because you might want models to like abstain from doing certain things if they think that they will do it incorrectly. But if they're not calibrated, they will not know what they're likely to do incorrectly. So this was not in the main text, but there were some really interesting things in the appendix about what do they call it, like selective prediction and what they call abstention predict precision and recall. So like two measures of like whether models can like abstain from answering certain things. So yeah, so those are figures 14 through 16 in the appendix. Pretty cool stuff, I think, but I will leave it to the viewer to check that out later. And then safety. Um, yeah, I'm trying to think, can I cover this? Probably not really, but I will say this is worth checking out. Like with the Tower Bench, they could examine trajectories for stuff like these are the good versions of this. So um, the opposite of doing this would be a compliance violation. So what a model should do is block unauthorized modifications. It should ensure correct transaction amounts. It should require identity verification, and then it should resist social engineering that tries to circumvent certain policies. And so if it fails to do that, it's a violation. And they do find that recent frontier models are better at doing this. And then the one thing I will say is previously, now like quite a few moons ago, we discussed this paper called safety washing that showed a correlation, a very high correlation between capabilities measures and safety benchmarks. And here, what they found was that financial accuracy, which again is this ensuring correct transaction amounts, was the most common failure. So that's like what drives this violation number. And that is really just a capability issue. So like this is very clearly um, like safety as capability, which does make sense if you're thinking about AI as a normal technology. And it is then worth pointing out that the lead author of this paper is one of the two AI as a normal technology guys. And if that AI as normal technology means nothing to you, I'll put something or Matt will put something in the chat about what that is. That's like a kind of I would say like a school of thinking, which is also a Substack. Um, written by two guys at Princeton.